A notation called Miller indices is used to indicate the different planes in a crystal structure. And these planes have different arrangements of atoms, different densities of atoms. And they're very important for X-ray diffraction. They're also important when you look at surfaces for catalytic reaction, many other applications. And so this video will describe the notation, and we'll use a cubic unit cell as the easiest one to explain the notation. And what we're looking at in this first problem is draw the 1, 2, 4 crystal plane. So the notation means that for the x direction, this is the inverse of the intercept of that plane with the x-axis. And this is inverse y-axis, inverse the z-axis. So 1 over 1, 1 over 2, and 1 over 4 correspond to the intercepts. So for the x direction, so x, y, and z in general, the unit cell dimensions a, b, and c. So this would be 1a, this would be 1/2 of b, and this would be 1/4 of c. So if I go back to my diagram, 1a, 1/2 b, and 1/4 c for the intercepts. This is the origin, x, y, and z direction. So 1a would be this point, y 1/2 of the dimension the b direction, so this point, and then 1/4 is about here. So if I draw this triangle that represents this plane, this would be the plane in this unit cell that has the Miller indices 1, 2, 4. And of course there's an infinite number, a very large number for a crystal structure. They're all parallel, so there'll be other ones in this unit cell, and then of course in the adjoining unit cells. So the question is, what's the spacing between those crystal planes with this Miller indices? And this says, and we're going to assume for this problem, we're going to use a cubic structure. It gives us, so this means A equals B equals C is 1/2 a nanometer. And so the spacing between the unit cells can be calculated from this distance in a cubic structure, and h squared plus k squared plus L squared. So Miller indice notation, this is h, k, and L. We're looking at the 1, 2, 4 plane, so 0.5 nanometers divided by the square root of 1 squared plus 2 squared plus 4 squared, which is 21, the square root of 21. If we do the calculation, slightly more than 1/10 of a nanometer. This is the spacing between the 1, 2, 4 unit cells. This, keep in mind, is for a cubic structure, and a cubic structure means the dimensions A, B, and C are all the same. So we'll look at one more example. Here we want to calculate the Miller indices if we're given a plane. So again, we have our crystal structure X, Y, and Z, and we want the H, K, and L values, the Miller indice notation, and they're in parentheses. So what we want to do is look at the intercepts. So for the x direction, plane intercepts, if our origin's here, so the origin is behind the plane, intercept in the x direction, so we're looking at intercepts. The x direction, it would be 1 times a. The y direction intercept, well, it doesn't intercept the y, so that's infinity. And the z-intercept is halfway up, so 1/2 of c. And what we're interested in, of course, is the inverse for Miller indices. So 1 over 1 is 1. 1 over infinity is 0. 1 over 1/2 is 2. So 1, 0, 2, these are the Miller indices for the plane in the figure. And again, there are parallel planes with this notation, and we could certainly go and calculate the spacing just like we did in the previous example. But these Miller indices are important, as we mentioned, for X-ray diffraction, determine where our diffraction peaks are, and for other applications, because crystal plane structures, slip planes, etc., depend on the direction and the particular crystal plane.